This video covers Part 2 of Section 3.3, Algebraic Structures. As a second example of an algebraic structure, we're going to look at the definition of a vector space. A vector space V over R consists of a non-empty set of objects called vectors on which two operations, addition of two vectors and scalar multiplication of a vector by a real number, have been defined satisfying the following axioms. We usually denote vectors with an arrow over the top, and we use letters such as U, V, W, etc. to distinguish them from numbers, which we refer to as scalars. So we have 10 axioms, and we'll denote them VS1 through VS10. The first axiom, VS1, is closure under addition, and this says for all elements U, V, and V, their sum, U plus V, is in V. VS2 is the commutative law of addition. For all elements U, V, and V, U plus V equals V plus U. VS3, the associative law of addition. For all elements U, V, W, and V, U plus V quantity plus W equals U plus the quantity V plus W. VS4 is existence of a zero vector. This states that there exists an element 0 in V, such that for all elements U in V, U plus 0 equals U. This statement has the symbolic form shown, and the element 0 is called the zero vector for V. VS5 is existence of negative vectors, so for each element U in V, there exists an element minus U in V, such that U plus minus U equals 0, and this has the symbolic form shown, and the element minus U is called the negative of U. VS6 is closure under scalar multiplication. For all vectors U and V, and for all real numbers K and R, the scalar product K times U is in V. So when we multiply a real number times a vector, we obtain a vector. VS7, the first distributive law, says for all real numbers K and R, and for all vectors U, V, and V, K times the quantity U plus V is equal to KU plus KV. VS8 is the second distributive law. For all real numbers K, L, and R, and for all vectors V and V, K plus L times V is KV plus LV. VS9, the associative law of scalar multiplication. For all real numbers K, L, and R, and for all vectors V and V, K times L times V is equal to K times L times V. And finally, VS10 is called the unit property, and this says for all vectors U and V, the real number 1 times U is just equal to U. To show that a set V on which operations of addition and scalar multiplication have been defined is a vector space, we need to verify that the 10 axioms in the definition hold. As with the definition of a ring, most of the axioms are statements involving only universal quantifiers. However, axioms VS4 and VS5 are both statements with mixed quantifiers. In VS4, existence of a zero vector, the existential quantifier comes before the universal quantifier. This means we have to find one element 0 such that for all U and V, U plus 0 equals U. The zero vector must be independent of U. In VS5, existence of negative vectors, the universal quantifier comes before the existential quantifier. This means we start with an arbitrary element U in V and then find a negative vector minus U for such a vector U. The negative vector depends upon the vector U, so for each vector U, we'll have a different negative vector. Note that the multiplication in a ring is defined between two elements of the ring itself. However, for a vector space, the scalar multiplication is defined between a real number and a vector, which are elements of two different sets. Examples of vector spaces include the set of ordered pairs of real numbers, the set of 2 by 2 matrices with real entries, and the set of polynomials with real coefficients. Note that the set of matrices and the set of polynomials are both rings and vector spaces. They satisfy both definitions. One of the most important examples of a vector space is the set of ordered pairs of real numbers, with addition and scalar multiplication defined component-wise. So let V be the set of ordered pairs of real numbers. So this is the set of ordered pairs A1, A2, where A1 and A2 are both real in R. And we define addition and scalar multiplication as follows. For all U equal A1, A2, V equal B1, B2 in V, and for all real numbers K and R. For the addition, we have U plus V is A1, A2 plus B1, B2 is equal to a1 plus b1, a2 plus b2. So we just add the two first components together and then add the two second components together. Scalar multiplication is defined by k times u equals k a1 a2 is equal to k a1 k a2. So we just multiply the first component by k and multiply the second component by k. Then v together with these operations can be shown to be a vector space. So for this example, we're just going to verify 4 of the axioms, vs1, vs2, vs4, and vs5. So for vs1, closure under addition. This states for all elements u, v, and v, their sum u plus v is in v. In symbolic form, we need to show for all u and v, for all v and v, u plus v is in v. So this is a universal statement, so we'll start with a proof by arbitrary element. Suppose u and v are arbitrary elements in v, and we need to show their sum, u plus v, is in v. Now since u and v are in v, this means that u and v are ordered pairs of real numbers. So therefore, u is equal to a1, a2, and v is equal to b1, b2 for some real numbers, a1, a2, b1, and b2. Their sum is then given by u plus v is a1, a2 plus b1, b2, which is equal to a1 plus b1, a2 plus b2. Now since a1, a2, b1, b2 are all real, then a1 plus b1 and a2 plus b2 are also real numbers. And therefore the sum, u plus v, is an ordered pair of real numbers, so belongs to v. And thus axiom vs1 holds. For vs2, we have the commutative law of addition. For all elements u, v, and v, u plus v is equal to v plus u. And in symbolic form, we need to show for all u and v, for all v and v, u plus v is equal to v plus u. So we'll again use a proof by arbitrary element. So we'll suppose that u is equal to a1, a2, and v equals b1, b2 are arbitrary elements in v. So u and v are supposed to be elements of v, so they're going to be ordered pairs of real numbers. And we need to show u plus v equals v plus u. So the left side equals u plus v is a1, a2 plus b1, b2, which is a1 plus b1, a2 plus b2. And the right side equals v plus u equals b1, b2 plus a1, a2, which is equal to b1 plus a1, b2 plus a2. Now, since addition of real numbers is commutative, then we know that a1 plus b1 equals b1 plus a1, and a2 plus b2 equals b2 plus a2. So u plus v is equal to v plus u. And this proves axiom vs2. For vs4, existence of a zero vector, this states there exists an element 0 in v, such that for all elements u in v, u plus 0 is equal to u. In symbolic form, we need to show the statement as displayed. So we need to show there exists a zero vector in v, such that for all u in v, u plus 0 is equal to u. The existential quantifier comes first, so we start with an existential proof. So we'll set up our two columns. We need to find a zero vector and then verify that it satisfies our two conditions. The domain is that 0 must belong to v, and the propositional function is that for all u in v, u plus 0 equals u. Since we want 0 in v, then 0 is to be an ordered pair of real numbers. So we can write 0 equals z1, z2, where z1 and z2 are the two real numbers that we're looking for. Now for all u equal a1, a2, 0 must satisfy the propositional function, which is u plus 0 equals u. And this is a1, a2 plus z1, z2 equals a1, a2. And on the left side, this will be a1 plus z1, a2 plus z2. And now we have two ordered pairs equal to one another. And so this equality holds if and only if the first components are equal, a1 plus z1 equals a1, and the second components are equal, a2 plus z2 equals a2. And the first equation implies that z1 must be 0, And the second equation tells us that z2 must be 0. And this shows that we should choose our z1 and z2 both 0, so that our 0 vector is the ordered pair 0, 0. So we've now found our 0 vector, and we're ready to verify that it satisfies our two conditions. So in the right-hand column, we have, since 0 is a real number, then 0, 0 is an ordered pair of real numbers, so our 0 vector belongs to V. For the propositional function, this is a universal statement, so we'll do a proof by arbitrary element. Suppose U is an arbitrary vector in V, then the left side, U plus 0, will be A1, A2 plus 0, 0, which is A1 plus 0, A2 plus 0, which is A1, A2, which is our original vector U. And this proves the propositional function. And so this shows that that 0 equal 0, 0 is a negative vector. I'm sorry, this should be a 0 vector for V. Therefore, axiom VS4 holds. So next, we have VS5, existence of negative vectors. And this states for each element U in V, there exists an element minus U in V such that U plus minus U equals 0, which has the symbolic form shown. So the universal quantifier comes first, so we start with a proof by arbitrary element. Suppose U equal A1, A2 is an arbitrary element of V. We need to show there exists an element minus U in V such that U plus minus U equals the 0 vector. And this is the 0 vector that we just found in VS4. So now we start an existential proof. So we need to find our negative vector, minus U, and then verify that it satisfies our domain and propositional function. So let's write minus U equals N1, N2. So minus U is supposed to be an element of V, which means it's going to be an ordered pair of real numbers. Then minus U must satisfy the propositional function, which is U plus minus U equals 0, which is A1, A2 plus N1, N2 equals 0, 0, which equals A1 plus N1, A2 plus N2 equals 0, 0. And so we have two ordered pairs equal to one another, and so this holds if and only if the first components are equal, A1 plus N1 equals 0, and the second components are equal, A2 plus N2 equals 0. Now we can solve these two equations for N1 and N2. We get N1 is equal to minus A1, and N2 is equal to minus A2. And this shows that we should choose for our negative vector, minus U is minus A1 minus A2. So we've now found our minus U, and we're ready to do the verification. And since U equal A1, A2 is in V, this means that A1 and A2 are both real numbers. So minus A1 minus A2 are also real numbers. And then minus U equal minus A1 minus A2 is in V, since it's an ordered pair of real numbers. For the propositional function, the left side is U plus minus U equals A1, A2 plus minus A1 minus A2, which is A1 plus minus A1, and A2 plus minus A2, which is 0, 0, which is our 0 vector. And so this equals the right side, so proves the propositional function. And this proves the existential statement. Therefore, minus U should be minus U equals minus A1 minus A2 is a negative vector for U equal A1, A2. So thus, axiom VS5 holds. Now, just as we did with rings, we can consider alternative definitions for the two operations for a vector space. For example, let's let V be the set of ordered pairs of real numbers with second component positive. So V is the set of ordered pairs A1, A2 such that A1 and A2 are both in R, and A2 is strictly positive. And we'll define addition and scalar multiplication as follows. For all U equal A1, A2, V equal B1, B2 in V, and for all real numbers K and R. For our addition, we have U plus V equals A1, A2 plus B1, B2 is going to be defined to be A1 plus B1 plus 1, a2 times b2. So instead of just adding the two components together, we're going to, in the first component, we're going to add the two first components and then add a 1. And in the second components, we're going to take the two second components and multiply them. And then our scalar multiplication is defined by k times u equals k a1 a2 is going to be defined to be k a1 plus k minus 1, and then a2 to the k power. So this is very different from the way we defined our addition and scalar multiplication in our first example. Then V, together with these two operations, can be shown to be a vector space. So we'll look at two of the axioms. So we want to verify axioms VS4 and VS7 for this example. For VS4, this is existence of a zero vector. We need to show that there exists an element 0 in V such that for all elements u in V, u plus 0 equals u. So we need to show there exists a zero vector 0 in V such that for all u in V, u plus 0 equals u. And the existential quantifier comes first, so we start with an existential proof. We set up our two columns, and we'll write for our zero vector z1, z2. And for all u equal a1, a2, our zero vector must satisfy the equality in the propositional function, which is u plus 0 equals u, which is a1, a2 plus z1, z2 equals a1, a2. And now we're using our definition in this example for the sum on the left. And so this will be a1 plus z1 plus 1, a2 times z2 equals a1, a2. And this holds if and only if the two components are equal. So that means that a1 plus z1 plus 1 equals a1, and a2 times z2 equals a2. Now in the first equation, we can cancel the a1s and solve for z1 to get z1 is negative 1. In the second equation, we can again cancel the a2s and we'll get z2 is equal to 1. So z1 is minus 1, z2 is 1, and this shows that we should choose for our zero vector the ordered pair negative 1, 1. So we've now found our zero vector. We're ready to verify it. And both minus 1 and 1 are in R, and the second component 1 is positive, so our zero vector, which is negative 1, 1, is in V, according to how V is defined. For the propositional function, we'll suppose u equal a1, a2 is an arbitrary vector in V, then u plus 0 equals a1, a2 plus minus 1, 1, which is a1 plus minus 1 plus 1, a2 times 1. And so in the first component, the minus 1 and 1 cancel, and we're left with a1. In the second component, a2 times 1 is just a2, and so we get a1, a2, which is our original vector u. And this equals the right side, so proves the propositional function. And this shows that 0 equal minus 1, 1 is a zero vector for V, and therefore axiom VS4 holds. Now note that to show our zero vectors in V, we need to check that it satisfies the conditions to belong to V, which means not only that it is an ordered pair of real numbers, but also that its second component is positive. For VS7, the first distributive law, we have to show for all real numbers k and r, and for all vectors u, v, and v, k times u plus v is equal to ku plus kv. So this is just a universal statement, so we'll use a proof by arbitrary element. Suppose k is an arbitrary real number, and u equal a1, a2, and v equal b1, b2 are arbitrary elements in V. And we need to show that k times the quantity u plus v is equal to ku plus kv. The left side is k times u plus v will be k times a1, a2 plus b1, b2. And so we do what's in the parentheses first, and so we're going to add the two vectors a1, a2 and b1, b2. using the definition in this problem, in this example. So this will be k times the vector a1 plus b1 plus 1, a2, b2. So now we have to use the scalar multiplication in this example. And so this will be k times the first component, a1 plus b1 plus 1, plus k minus 1, and then a2, b2, the second component, raised to the k power. And we can simplify this a little bit. This will be ka1 plus kb1 plus 2k minus 1 in the first component. And in the second component, this is a2 to the k times b2 to the k. And the right side equals ku plus kv will be ka1a2 plus kb1b2. So for the right side, we're going to do the scalar products first. And so the first one is ka1 plus k minus 1, a2 to the k power. And the second is kb1 plus k minus 1, b2 to the kth power. Now we want to add these two vectors together. And when we do so, we obtain ka1 plus k minus 1 plus kb1 plus k minus 1 plus 1. And then in the second components, we multiply the two together, and we get a2 to the k times b2 to the k. And we can simplify the first component a little bit more, and this will be ka1 plus kb1 plus 2k minus 1, and the second component, we just leave it alone. And now comparing the two calculations, we can see that the two sides are equal, and this proves axiom VS7. And so that's 2 of the 10 axioms for this particular example. And so after we verify the other 8, then we can conclude that this gives us a vector space. So even though this is sort of a strange addition and a strange scalar multiplication, it still satisfies the axioms, and so it still gives us a vector space.